welcome to Algebra II with Mr. Clausen. Today I want to talk to you about getting started with real-world exponential models. And what I want to go over today is just a couple simple real-world models that we can look at and how exponential models can be used in the real world. And so this is expounding on the knowledge in the previous video that I made. So if you haven't seen that yet, I would encourage you to watch that one first, because that is designed to supplement the content I'm going to talk about here. And so what I want to do here today is go over a real world example and how we can set up a given set of information and plug it into an exponential model, because it is a relatively simple process that this type of system can be applied to. So we're going to look at a couple examples how we can do that and plug it in. And so one of the things I want to look at is a population example. So for example, the world population in 1999 was approximately 6.08 billion people, and the annual rate of increase was about 1.31%. Okay, these are just made up numbers, relatively close to what they actually are, but we can actually take these numbers and plug them into a exponential model, which is just a simple y equals ab to the power of x model. In my previous video, I talked about each of these variables and what they represent, and what we're going to do is we're going to actually take that knowledge and apply it to the situation. So if we want to go and we want to find a growth factor is going to be what I would refer to as a rate. And we talked about that the rate of increase is a growth type function, which is what this is representing. And the growth of this is going to be the decimal form of the increase. So what I see here is that this is 1.31%. And in decimal form, 1.31% would be equivalent to 0.0131. Okay. And the reason that this is important is that if we're talking about a growth factor for a given function, this is what we use to find out what the b value should be. Okay, so the b value tells you your growth or decay of a given function, and the a value usually indicates a starting value. And so what this will allow you to do is that as you go and you look at a given set of data as such, what we can do is we can find the rate. The rate can be plugged into the b value of the equation, which is going to be 1 plus r. Because the thing is that if you have a population of 6.08 billion and the increase of the population overall, including the people that pass away, is 1.31%, you're going to have your 100% of your population that you started with plus the rate of increase or decrease, depending on the situation that you have at hand. And so if we understand what the r value should be, what the rate of increase is, we can then use that to find the b value. And the b value in this given case would just be equal to 1 plus 0.0131, and this can be equal to 1.0131. All right, and suppose the rate of increase continues to be 1.31%, write a function to model the world population growth. All right, and this is where we can start combining some of this stuff. So again, if you are trying to make an exponential model, y equals a times b to the x power. B is my growth factor. So I know that b is equal to the growth factor that I just created, the 1.0131. Because if I multiply any number a by this for 1 year, like assume x is equal to 1, that would represent the 100% that I already have plus the rate of increase that's being indicated. So the a value for any exponential model is always going to represent the starting population or amount. And I'll just say or amount here, because if you have like a substance and you're like amount, and you are watching it grow or decay over time. That's another way that you can look at it. So the starting amount in this given situation is just simply 6.08 billion. And so if you want to make a function to represent the world population as the years progress, all we need to do is go y equals 6.08 times 1.0131 to the x power. And what this function represents is that after x number of years, we can model the behavior of the population based on these relative increases, right? So you have your growth, you have your initial population in billions. And so what y will give you is billions of people after x years. And so now we can take something such as this, we can plug it into Desmos, we can use other graphing capabilities, and we can go and represent this particular function. All right, and so what you can see here, if we plug this data into Desmos, is that we have 6.08 billion right here. And let's say after 100 years, with the 1.31% increase, we would have close to 22 million people in our population after the given amount of time. So it can be a really useful way to extrapolate some predictions and to take into account a growth factor if the growth factor stays consistent. So another example that I want to go over, this is a business example, and this is a specific situation that you actually might find pretty relevant as well. And this is a depreciation example. So here I have a situation where you have a $12,000 computer at a time of purchase, and it depreciates at a rate of 14.3% per year. And what we can do with exponential models is we can actually go and create a function that describes this depreciation. And again, so since we have a 14.3% decrease, this is representing a negative value, so it's representing a decay type function. And so if you remember, when we're trying to find the b value, this is going to be 1 plus r, and since it's a decay value, r is negative. R in this case is the decimal form of 14.3%. So we can say 1 minus 0.143, and this would be equal to 0.857. And this would be the b value for your given situation. And in the previous example, we talked about A being a starting population or amount. Well, this is the starting amount of money that your computer's worth. So in this case, A is equal to $12,000. So what we can do is, remembering that y is equal to a times b to the x power, y is equal to $12,000 times 0.857 to the x power. And again, what you'll have is that you'll have the initial value of your computer, you'll have the decay function, or decay factor, I should say, and you'll have years old. So this is how many years old the computer will be, and then this will be the value of your computer after X years. All right. And so now it says define the value of the computer after 3 years. So what we can do is we can say, and we could even put this in function notation. We could say something like value of X equals $12,000 times 0.857 times X. And then say when the value, what's the value of the computer after 3 years? Since we've been doing a lot of function notation, why not use it? Take that to the third power. And so what we would need to do is we would need to solve for this, and the value of this computer after 3 years would only be $7,553. And let's go to the nearest cent, since that's kind of how money is used. And so what you can see is that if we plug in the graph from Desmos here, you'll see that at the initial purchase, at 0 years after you buy it, it's worth $12,000. And then the moment you take it home and you plug it in and you go and play with it for a year, it decreases in value very quickly. And after 3 years, you get the price that we talked about here. After 10 years, it goes and decreases to $2,500. And then after 15 years, it is only worth about $1,200. And so the exponential model can take things that have a typical depreciation, and you can go and model that in different ways. So with that said, I'm going to conclude this video here. I hope that you found this video helpful in understanding how to set your A and your B value of your exponential models. And with that said, let's do some math.